Okay, so in this video what we're going to discuss is the mechanism of action of two drugs, namely amiloride and triamterene. Okay, so amiloride and triamterene, and basically they have exactly the same mechanism of action. So triamterene. Okay, they're both used as diuretics, and diuretics means that they promote diuresis, and diuresis is the passing of urine. So these drugs somehow are going to make us excrete more water. And the way they work is by acting on the same cells that we've discussed in the previous videos on the renin-angiotensin-aldosterone system. So basically, in the kidney we have loads and loads of nephrons. So let me draw a nephron. So here is Bowman's capsule. Here is the proximal convoluted tubule here. So Bowman's capsule ends and you have the proximal convoluted tubule. And then it goes into the loop of Henle, the descending loop of Henle first, and then it ascends back up. So we have descending loop of Henle and then ascending loop of Henle. And then it forms the distal convoluted tubule here. Okay, and then finally the distal convoluted tubule ends and forms the collecting duct, which then drains what is left into the renal pelvis. So let's label this diagram up. So this is the collecting duct. This is the distal convoluted tubule here, and convoluted just means that it curves in the way that I've drawn. Distal convoluted tubule. This is the ascending loop of Henle here. Ascending loop of Henle. And this on the other side is the descending loop of Henle, because obviously in this point the filtrate will be moving this way and it will be descending, so that's the descending loop of Henle. And then finally we have the proximal convoluted tubule over here. Right, so the site of action of the drugs amiloride and triamterene is in the distal convoluted tubule / cortical collecting duct. So let me just finish writing this. Proximal convoluted tubule. Okay, so the distal convoluted tubule at the end of the distal convoluted tubule, so in this sort of region, is obviously continuous with the cortical collecting duct. So the cell types in this portion are similar. So you have a cell that looks like this. So we've bumped it up hugely, obviously. This would actually be tiny compared to this drawing. But we've got this massive great cell, which we're going to use to represent a small one of these down here. And this is going to be a cell that basically lines the late distal convoluted tubule and the early cortical collecting duct. And basically it's these cells which amiloride and triamterene are going to act on. Now these cells reabsorb salt and water basically from the lumen, and triamterene and amiloride are going to block that reabsorption. So the way that these cells reabsorb sodium is that they have in their basolateral membrane a sodium-potassium pump which moves 3 sodiums out and 2 potassiums in, and then in the apical membrane they have a very special sodium channel called the epithelial sodium channel, which has a structure, and I just want to go over the structure of the epithelial sodium channel. So the structure of the epithelial sodium channel is that it's made up of 4 subunits which are homologous to one another, so they're very similar structure, and basically they line a central pore which is in the middle. So you've got one subunit here which is an alpha subunit, so this is an alpha subunit here, so this is alpha. Then on this side you have a subunit which is called a gamma subunit. You have another one back here which is an alpha, and then another one to the side over here which is a beta subunit. So basically overall the epithelial sodium channel is made up of these 4 subunits which are bonded together, and you can see that they form this pore in the center through which sodium cations can move. So this is the structure of the epithelial sodium channel. Often abbreviated to ENaC, epithelial sodium channel. Okay, so these epithelial sodium channels are placed in the apical membrane of this cell. So these epithelial cells have tight junctions between them, and that means that the cells become polarized. So we have an apical membrane and a basolateral membrane, and the membrane-bound proteins in the basolateral side cannot go into the apical side. So they are two separate portions of membrane which are not continuous with one another. So membrane-bound proteins that are put in one will stay in that one and can't move into the other one. So you can put these epithelial sodium channels, which for the basis of this picture I'll just draw like this, into this apical membrane, and you can have the sodium-potassium pump restricted specifically to the basolateral membrane. So ENaC is in the apical membrane, and the sodium-potassium pump is in the basolateral membrane. And that's the genius of epithelia, that because of this polarization of the cell membrane, you can restrict the sodium channels to be in this apical portion of the membrane, and the sodium-potassium pumps to be in this side of the membrane. Everything else about them is just not what happens in all cells, basically. You also have obviously a potassium channel here, which we'll just call the KC, the potassium channel, which allows potassium to move out of the cell. So basically, after that, it's just what happens usually in cells which have a resting membrane potential across their cell membrane, i.e. sodium moves into the cell through the sodium channels, because sodium is kept very low inside the cell and high outside the cell. So sodium is going to move through these channels into the cell membrane. Similarly, oppositely actually, potassium is going to move out of the cell through its channel, because potassium is very, very high in the cell intracellular environment and very low outside, so it's going to move out of there. Now, the amount of sodium moving in balances the amount of potassium moving out. So overall there's no movement of charge across this cell membrane. However, if you keep this up, what's going to happen is you're going to drain all your potassium out, and you're going to drain a huge amount of sodium in. So sodium concentrations are going to go high in the cell, and potassium concentrations are going to decrease in the cell. So to keep an ionic balance here, you also have this sodium-potassium pump, which throws sodium out of the cell and moves potassium back into the cell to counteract the effect of these channels, basically. And the genius of epithelial cells is that you put the sodium channels on one side and the sodium-potassium pump on the other side, and that overall means that when this process goes on, which goes on in all cells, but in this case you're overall going to now move sodium from one side to the other, but that's because of the fact that you have isolated these channels to one side and the pumps to the other side, and that's what doesn't happen in normal cells. In normal cells, the pumps are interdigitated amongst the channels. So basically you're just throwing the channels allow the sodium in, and then right next door the pump is then moving the sodium back out. So that's the genius of these epithelial cells. So this is how these cells in the late distal convoluted tubule and cortical collecting ducts absorb sodium and move sodium from the lumen to the basolateral side. So they move sodium over here. Then what they have is chloride channels, which allow the chloride to move. And basically, because the glomerular filtrate in this luminal side will contain not just sodium ions, but it will contain the counterion, and the counterion to sodium usually is chloride. So basically what will happen is, if you gradually move sodium to this side, you're going to gradually build up a positive electrical potential here, because that's what this overall does. If you ignore the details, what's actually happening here is you're going to move sodium from here to here. The potassium is just going round in a circle. Now that's usually what happens in cells for sodium as well, but because of the polarization of the cell, because of these tight junctions, that isn't happening. Sodium is actually being moved across the membrane, across from the apical side to the basolateral side. So you build up this positive electrical potential on the basolateral side, basically, and that pulls the chloride anions towards it, because the chloride anions are still here, and you're also going to, obviously if you've moved sodium from here, the chloride anions are still over here, so they have a negative charge on, so you actually end up with a negative charge over here as well. So the chloride channels have got an electrical potential difference that is driving them to move from the lumen to the basolateral side. So basically all the cell then needs to do is put in chloride channels on both the apical membrane and the basolateral membrane, and then you just let electrostatics, or electrodynamics maybe in this case, do its work basically. The chloride will move through this channel here into the cell, and then it will move out of the cell and into the basolateral space in order to be with the sodium, basically. Okay, so then overall what you've managed to do is move sodium and chloride across this membrane, and now the final step is that water will now follow that. Because overall now what you're doing, what this cell has done so far in this story, is that it's moved salt from the glomerular filtrate to this basolateral surface. Now, basically, that means that the osmolarity of this glomerular filtrate is going to go down, i.e. that the amount of molecules, molecules dissolved in it is going to go down, and over here the osmolarity is going to go up, the amount of molecules dissolved in it is going to go up. So water will then move from osmosis from the area of high water potential, where the water has very little solute, to the area of low water potential, where the water has more solute. So water ends up moving via osmosis. And as I've already said, my favourite explanation for why osmosis happens is that if you have two compartments, one which has a very high sodium chloride concentration in, and one which has a very low sodium chloride concentration in. So let's say compartment 1 has a low concentration of sodium chloride, and compartment 2 has a high concentration of sodium chloride. Well, basically, sodium chloride is an ionic compound. You have a sodium ion, which has a positive charge, and you have a chloride anion, which has a negative charge. So this is negative and this is positive. And basically, when you dissolve sodium chloride in water, these two no longer stay sitting next to each other. In the great big, when you have salt, when you put salt on your food, the crystal salt, what that is effectively is it's absolutely loads of these in the great big lattice. So you have a sodium chloride next door, and it just goes on in a great lattice basically. You'll have another green one there, more orange ones above. So that's what normal salt is. However, when you dissolve salt in water, what happens is that all of these bonds between the sodium and the chloride are broken, and the reason is that water is an incredibly polar molecule. So the oxygen atom in the water molecule ends up sort of stealing the electrons from the hydrogen. It's not as extreme as an ionic bond. In an ionic bond, the chloride atom actually does take the electron from the sodium, but in these covalent bonds, they are less extreme versions of ionic bonds. So basically, oxygen likes electrons better than hydrogen, and exerts a greater pull on the electron than the hydrogen. So what ends up happening is that it's oxygen exerts a greater pull on the electrons than the hydrogen, and basically the electrons spend more of their time around the oxygen than they do around the hydrogen. So in these covalent bonds, really what you have is you have an electron from the hydrogen and an electron from the oxygen, in both cases, like that. Okay, so that's a dot-cross diagram. The dots represent the electrons from the oxygen and the crosses represent the electrons from the hydrogen. But basically these electrons in these bonds, they prefer spending their time closer to the oxygen atoms than they do spending the time closer to these hydrogen atoms. So what you end up with is basically the hydrogen atoms get a slight positive charge, and the oxygen gets a slight negative charge because the electrons are spending their time over here, and obviously the hydrogens are just left with their proton right at the center, which has a positive charge. So water ends up being a hugely polar molecule, and this means that the water can interact with the electric charges on the sodium and the chloride anions. So basically what you end up with is sodium atoms surrounded by water molecules like so, where the oxygen faces in towards the sodium ion at the centre there, and the hydrogens face away, and you form these large sort of complexes of ions surrounded by water molecules. Okay, and a similar thing happens for the chloride anions, except the opposite way round. Basically, you'll have a chloride anion at the centre, but this time the hydrogens will face the ion and the oxygen will face away. So you basically have something that looks like this. Right, and you can continue on the picture. Okay, so what this overall core means is that on this side, where you have a very high concentration of sodium chloride, more of the water molecules are going to be bound to these ions in this way. So you're going to have huge, great complexes of ions surrounded by water molecules, and you're going to have fewer water molecules that are actually free and on their own, basically, because most of the water molecules are going to be bound with these ions in this way. Whereas on this side, you're going to have far fewer of these complexes and more water molecules that are just free and off on their own. So, if you put in a membrane down the middle of these two compartments that allows water to move, but doesn't allow these massive great complexes to move, so basically this entire complex of a sodium atom with all the water molecules surrounding it can't go through this membrane, but these free water molecules can, basically. If you put in a membrane like that, and also, obviously, this membrane doesn't allow sodium atoms, sodium ions and chloride ions to cross. If you put in a membrane like that, what's going to happen? Well, there are more free water molecules on this side than there are on this side. So overall, the number of water molecules on this side that are going to move from 1 to 2 is going to be some size. So a certain number are going to move from 1 to 2. And also, some of the water molecules on side 2 will move to side 1. However, the number that move from side 2 to side 1 is going to be less than the number that move from 1 to 2, simply because the number in here that are actually capable of moving is bigger than the number in here that are capable of moving. So it's not that there's some fancy force thing going on here, it's just that probability says that there are more water molecules here, so the chance of a single one crossing is going to be greater than the probability of a single one crossing on this side. So overall, the number that cross from 1 to 2 is going to be bigger than the number that cross from 2 to 1. So that overall means that there is a net movement of water molecules in that direction, and that is the principle of osmosis, the fact that water is moving from where there is a low solute concentration to where there is a high solute concentration. So basically, once you've moved the sodium chloride and you have a high solute concentration over here, your cell effectively acts like this semi-permeable membrane that will allow the water molecules to move, but not these huge great complexes, and water is going to move in this direction as well. So here is our net movement of water. Okay, so overall what you have now done is you have moved sodium chloride and water across your membrane. You've absorbed it from the lumen of the nephron. Okay, it's basically this process that these drugs are going to target. These two drugs are going to stop this reabsorption of sodium, and therefore they're going to stop the reabsorption of chloride, and therefore they're going to stop the reabsorption of water. And if they stop this reabsorption of water, then the water and the salt are just going to continue on through the collecting duct and end up in the urine. So you're going to produce a greater volume of urine, basically. So, the way that these two drugs, amiloride and triamterene, both work is that they bind to the extracellular, so to the luminal side of the epithelial sodium channel, and they block sodium from being able to go through. So basically, on this picture, what they do is, let's draw a big molecule blocking that lumen. So let's put in a big molecule that's going to block that lumen, and then no sodium can go down that pore anymore. So this represents our amiloride or our triamterene. Amiloride or triamterene. And they both act in exactly the same way. So they both bind to the extracellular domain of the epithelial sodium channel, and they block the sodium from being able to go through. And if you block that sodium from being able to go through, then you block this process. You block this movement of sodium from the luminal side to the basolateral side. If you block the movement of sodium, then you don't build up this electrical potential difference between the luminal side and the basolateral side. If you don't build up the electrical potential difference, then there is no driving force for chloride to move from the luminal to the basolateral side. So chloride doesn't move. So overall, you don't get any movement of sodium chloride. And if the sodium chloride remains in the lumen, then the water will remain with it because there's no osmotic driving force to move the water. So you overall end up excreting more water, and you urinate more, and that's known as the process of diuresis. So these drugs, amiloride and triamterene, are both diuretics.